a common thing one notices in the educational system is that a student is extremely interested to start with, but as he progresses, as he finishes his course, by the time he has completely lost his interest. Be it biomedical engineering, be it mechanical engineering, it's always the case. The problem is that the student doesn't know why something is there in the syllabus and why he is reading it when he is reading it. The result is that, say, we end up with mechanical engineers who doesn't know the difference between a 4-stroke and a 2-stroke engine. Or at a graduate level, the PhD student at his 4th or 5th year doesn't know what his PhD question is. The objective of this video is to avoid such things in biomedical engineering. In this video, I'm going to give a big picture of biofluid mechanics. Essentially, I'll briefly review what biofluid mechanics is, and time permitting, I will also introduce some open problems as well as some cutting-edge medical devices that are currently in use or almost going to be in use pretty soon. With that, we'll get started. Very briefly, we have flow properties of blood over here, and fluid dynamics in the cardiovascular system, as well as some properties of arteries. What I'm going to do is to scan through each of these topics and give a review of them over here. I'm going to give minimal information here in this video. If you need more elaborate information, I'm going to refer previous videos that I have made. And in addition to that, so in most of my videos, I have polls at the top of the question. So these are not just polls, these are most of the time conceptual questions to test or improve your understanding. So I always suggest that you take a look at the polls that I have over the course of a video, and also these polls or questions are also extremely timed well to appear at a certain point in the video. First thing, let's look at laminar flow. Laminar flow, say let's take a part of a blood vessel. We are going to assume the flow is laminar and say it's going to be parabolic. The relationship between change in pressure at the two ends is going to be proportional to the flow. Proportionality constant is the resistance given by 8 mu L by pi r naught power 4. The key thing is this: we are going to assume the velocity is parabolic, and with that we can derive this expression for resistance. Once we assume the flow is laminar and we have an expression for the resistance, it's easy to analyze, say, series of blood vessels or network of blood vessels or blood vessels in parallel, as in the case of grafts. The next straightforward generalization from the laminar approximation is to look at a variable cross section. Instead of assuming it to be a straight tube, we are going to assume the tube is going to be of a variable cross section. And the equation that comes very handy in analyzing this situation is the very well known Bernoulli principle. Essentially, in problems involving pressure and velocity at one cross section and pressure and velocities at another cross section, can be related using the Bernoulli's equation, and unknown variables could be easily found. An additional equation that is usually required while using the Bernoulli equation is the equation of flow conservation. Essentially, flow is velocity times A1. So flow here is flow equal to flow here. Given this, we note velocities and geometries are related at these two cross sections. With these two equations, we could solve most problems involving pressure and velocities variations at two cross sections. And devices like venturimeters are all designed based on this principle. See, as we are making assumptions like laminar and steady state and all that, we want to make sure those assumptions hold good for the problem of interest. And that's why we need to always check. These two numbers, these two non-dimensional numbers, are of great importance. First is the Reynolds number, the ratio between the inertial forces at the top and the viscous forces at the bottom. If the Reynolds number is too low, flow is going to be very nice. Take honey for example, or even a glass plate. The flow in them is extremely nice. On the other hand, consider water in a waterfall. There the Reynolds number is pretty high, and flow is turbulent. The Reynolds number could also be expressed using, this is velocity v times diameter d, and nu is the kinematic velocity, which is nothing but this term. The alpha over here is what is known as the Omerselli number. It defines whether a flow is pulsatile or more steady. Okay, essentially it's the ratio between transient inertial forces to viscous forces, the nu we have over here. Okay, so for example, in blood vessels like the aorta and major arteries, flow is going to be pulsatile, while in blood vessels like capillaries, okay, flow is going to be pretty much slow. So in aorta, this number is going to be very high, close to 15. In capillaries, this number is going to be orders of magnitude less. Okay, so with these two numbers, pretty much we can define what the flow regime is, define whether the flow is laminar using the Reynolds number, and define whether the flow is pulsatile using the Omerselli number. Having said that, the most important number over here is this term called the viscosity of blood, okay, which is what we are going to see next. Viscosity is essentially the proportionality constant between shear stress and the gradient of velocity. Okay, the viscosity is too high, like honey. Okay, it's going to be difficult to shear the fluid. It's like water. Viscosity is very less. It's going to be very easy to shear the fluid. You can always rewrite velocity and shift the derivatives over here. The term we have here is known as the shear strain. Okay. And if we use the derivative of shear strain in this definition, we get viscosity is also acts as a proportionality constant between the shear stress and the rate of shear strain. Okay. So if we take, say, so we consider, let's say, the shear stress in this axis and the strain rate in this axis. Okay. And let's consider log-log scales, okay. So this is going to be in log and this is going to be in log. If it were like normal water, the plot here would look something like this, okay. So this is just for water. But blood is not like water, blood is more like sambar, okay, with all those cells and proteins in blood, okay. So based on that, the actual viscosity of blood is going to depend on the shear rate, okay. And the actual dependence would look something like this, okay. At very low shear rates, we have very high viscosity, and at very high shear rates, we have lower viscosities, okay. This is what is known as a shear thinning liquid, and there are various mathematical models to approximate this behavior. And one could go ahead and ask, why this kind of behavior? Okay, essentially the actual viscosity is a sum of two terms. The water content in blood plus the red blood cells affect the viscosity. Essentially, at lower shear rates, the red blood cells form what is known as a Rowley-X. Okay, these patterns, they clump together and increase the viscosity of blood. On the other hand, at very high strain rates, they don't clump together anymore and result in a lower viscosity. And we also know that this viscosity depends on a couple of other factors like, say, temperature, a couple of proteins in the blood, even platelet adhesion and things like that. So with this, we could say many things. For example, say someone has problems with the red blood cell, say there is anemia, sickle cell anemia, okay. Their viscosity is going to be drastically different and hence their hemodynamics is going to be different. First thing. Second, there are many cutting edge research that's going on concerning viscosity of blood. Okay, there is this condition known as sepsis where it's very hard to predict particular disease is going to get fatal or it's not going to get fatal. Recent research has shown that if we do some kind of viscoelastic measurements with blood, specifically while it's clotting, we get prognostic information on whether a disease is going to get fatal or not. Okay. Interestingly, this device is not yet in wide use in India. Having said that, we got pretty much the blood covered. As far as blood, as well as most soft tissues are considered, okay, if we look at the strains here and the stresses here, there is usually a phase shift. Okay. For example, if you had to consider an analogy with electrical circuit, if we have purely a resistive circuit, there is not going to be any phase shift between V of t and I of t, right? But if you have terms like a capacitor, okay, there is going to be a phase shift between velocity and current. Similarly, there is going to be a phase shift between the pressure head and the flow. In order to model that, in addition to a resistor, we also need capacitance-like terms that describe stresses and strain, and that's why we need viscoelastic models. Okay. And while we are discussing about viscoelastic models, I'm going to also mention about a better approximation for blood vessels, which are known as the Bind-Kessel model. If we take a blood vessel, segment of a blood vessel, and approximate it by a purely resistive circuit, that does not suffice for many practical purposes. What we need is to approximate a segment of a blood vessel by a resistor, a capacitor, grounded capacitor, and a resistor. Such models usually are known by the name of Bind-Kessel models. Having said that, the next obvious thing is to study what happens to the vessels where the actual flow happens. So far we have been looking at flow properties of blood. Okay? That blood flows in blood vessels, and it's also important to look at what happens to the vessels. The integrity of the cells that line the blood vessels depends on the stresses in this direction. Okay? If these shear stresses are too high, they might disintegrate or get damaged. Okay? So in the wall, shear stresses are given by pressure gradient times R0 by 2. And as far as blood vessels are considered, if we look at them as pressurized vessels, okay, what are the stresses that are highest in a blood vessel? It's the hoop stress. Hoop stress or stresses along the circumferential direction, okay, they are given by pressure times R0 by the thickness of blood vessels D, okay, and the hoop stress are usually the highest. They are in fact twice as large as the stresses in the longitudinal direction. There is one more stress in three-dimensional, which is the radial stresses, which are usually pretty low unless we are studying shock wave propagation in, say, aortic dissection. So we can study blood vessels as a pressurized vessels, and while doing that, the elastic properties of the blood vessels become extremely important. Okay, and how do we characterize the thickness of the elastic properties of a blood vessel? We use the pulse wave velocity. Okay, we know pulse wave velocity is given by square root of ED by rho d. This is like the relationship between bulk modulus, density, and say speed of sound. This E is essentially elastic modulus for the entire blood vessel, change in pressure over change in volumes. So this elastic modulus is defined for the entire blood vessel. But if we take a small part of the blood vessel or most biological tissues in general and plot stress versus strain, okay, elastic modulus is the slope of this curve at any of these points. And for most soft tissues, this relationship is going to be exponential, and we have models like Fung type materials to describe this behavior, say in 3D. Okay, we discussed about stresses, strains, and say the hoop stresses and the longitudinal stresses. At this stage, one might ask, what is the maximum stress anywhere at any given point in the tissue of interest, or what is the minimum stress in the interest? The way to answer this question is using what is known as the Morse circle, and I refer to the video that I already made on this. Okay, and finally, does viscoelastic and soft tissue model suffices to model biological tissues? The answer is no. If we take any blood vessel, okay, there is a particular layer known as smooth muscle cell. Okay, they expect a specific pressure to be acted upon in the blood vessel. Pressure is too high or low, they are going to change the diameter of the blood vessel. So they are active, okay, and they will change the diameter of the blood vessel. To model such response, or say to model a beating heart, we need what is known as active muscle models. With that, we are moving towards the mechanics of the heart. Concerning the heart, we need to know a couple of basic things. Okay, what are ECGs and what are the pressures? So when someone says they have a pressure of 180 over 80 mmHg, okay, what is 120 and what is 80? Essentially, the pressure is inside the heart is going to be dynamic because it keeps on beating, so it's going to rise and fall. Okay, and for practice, I suggest you go and check what this 120 is
in this curve and what this AT is in this curve.
I'll make a separate video on that.
Regarding ECGs, we need to know what P, Q, R, S, T signals are. Okay, and we can estimate, say, the heart rate by looking at distances between two consecutive heart beats. So we can estimate heart rates from ECGs. And one of the most important hemodynamical quantities of interest concerning heart is this thing called the cardiac output. Okay, cardiac output is given by stroke volume times the heart rate. If we look at any heartbeat, the heart is going to relax, blood is going to get filled. Okay, it goes into a diastole. Then it starts pumping. As it pumps, the volume becomes smaller and smaller and smaller as the heart beats. Okay, and there is a change in volume in each heartbeat. That volume is known as, the change in volume is known as the stroke volume. And stroke volume times the heart rate will give the amount of blood the heart pumps. That's known as the cardiac output. How is cardiac output measured? Initially they used methods based on thermal dilution, but these days we mostly determine cardiac output from echocardiography. Okay, from echo images. Okay, and finally the amount of oxygen concentration, the partial pressure of oxygen in the blood is also of interest, say during surgeries and all that. For that reason, measurements on blood gas is of importance. Okay, so I pretty much covered most topics, say in the biofluid mechanics syllabus. I'll conclude this video with a brief introduction on various biomedical devices used specifically within the cardiovascular system. Okay, the first thing is, of course, heart is a pump. We have artificial pumps for the heart. Okay, and heart is also an electrical conduction system that keeps track of its own rhythm. Okay, that rhythm can be abnormal at many times, and we need pacemakers to correct that. For biomedical engineers, I suggest you get to know the difference between what a defibrillator is, what a pacemaker is, and perhaps get to know on terms like cardiac resynchronization. The pumps and the pacemakers make up the medical devices within the heart, and some of the devices used within the blood vessels include, say we have a blocked blood vessels. Some of the common things to do is to put a stent and remove this block. Okay, so that's why we get stents, or alternatively one could add a additional route for flow of blood. Okay, so these are known as grafts. Okay, it's a bypass grafts. Say if the walls within the blood vessels or in the heart are damaged, say the aorta is damaged, we can replace them with artificial valves, or we can use clips for valves like the mitral valve. Let's see the topics that I haven't covered yet. Okay, one is fractional flow reserve and intravascular ultrasound. These two topics deserve a separate video, so I am going to discuss them in a part 2 of this particular video. I have shared all the references that I used to make this particular video, along with the references that discuss some of the open questions that I mentioned in this video. Finally, okay, thanks for watching. Let me know if you found this video helpful, whether it gave you a big picture on what biofluid mechanics is, whether it got you curious. Okay, if you find this video really interesting, please share this with your friends who are starting to do biomedical engineering, or even those who are deep into biomedical engineering. What else? If you think they are not yet really interested in the subject.